Hello. Okay, so let's start by reviewing what we did in the previous lecture. We talked about projectors or projection matrices, and a projector is a square matrix n by n that is idempotent. And every idempotent matrix is a projector. So basically, a projector if and only if idempotent, which means that p squared is equal to p. And the meaning of this is that this projector matrix, it projects specifically, so it projects onto the range of the matrix along the null space of the matrix. And if you project a vector, it basically gives you the component of the vector living in the range. And if you project the projection, okay, which means that you apply to the vector p squared, then the second projection will do nothing. Okay, so that's the meaning of p squared equals to b. It means that if you have a vector x, so you project x using px. So this is now the projection. This lives in the range of p. If you project again, okay, so you project b of x, this is b squared of x. I mean, the second step will change nothing because the projection is already in the range of p. Okay, so that's like sort of, if you want, like what is the meaning of a projector if and only if it is idempotent. Now, the range of B and the null space of B are not like arbitrary, so they must basically satisfy the following. Their intersection, okay, so these are two subspaces. Their intersection should only be the all zero vector. So the intersection is trivial. And you can take any arbitrary vector in the n-dimensional space and express it as the sum of two vectors, one of them living in the range and the other living in the null space. Okay, so for projectors, we have this important property. Again, the range, the intersection of the range and the null space is just the all zero vector. And you take any vector in the space, you take vector x. You can express it as follows. You take x, you write it as bx. Okay, of course, x is not equal to bx unless x lives in the range of b, but for a general x, you have here bx, so you add x and you subtract bx. And so this is equal to bx plus identity minus b multiplied by x. So what is this first vector? This first vector is p multiplied by a vector, so it is living in the range of p. And what is this other vector? It is a vector in the range of I minus p. And in the previous lecture, we proved that the range of I minus p is exactly the null space of p. Okay, so we have these two important problems. And generally when we have a projector onto S1 along S2, it must be the case that S1 intersection S2 is just the all zero vector, and it must be the case that any arbitrary vector in the space can be written uniquely as basically two components or two vectors, one in S1 and one in S2. A projection matrix is guaranteed to be diagonalizable. The eigenvalues are ones and zeros, and basically the number of ones is the rank of the matrix P, which is the dimension of its null space. If you start with a vector living in the range of P, then P multiplied by X is equal to X. If you apply a matrix norm to B, and here there is, if P is the all zero matrix, which is basically sort of a trivial projector, it's a projection matrix in which there are no one eigenvalues, or the eigenvalues are zero. If we exclude this case, then a matrix norm applied to a projector should always give you a result greater than or equal to 1. P is a projector if and only if I minus P is a projector. Okay, and so basically here I minus P swaps the roles of the range and the null space. Okay, so if P is a projection onto R of B along null space of B, then I minus P is a projection onto the null space of B along the range of B. Okay, and this property here is sometimes very useful. right? Because if you know that P is a projector, then automatically I minus P is a projector and vice versa. Now, what about orthogonal projections? Note the following. I mean, for some reason, some people always get confused about this. When I'm talking about an orthogonal projection matrix, I am not. This orthogonal is an adjective for projection. It's not an adjective for matrix. Okay, so an orthogonal matrix, we know what is an orthogonal matrix. It's a matrix. You know, Q is orthogonal if Q Hermitian. This is for the real case. So Q transpose Q is identity is equal to Q transpose. That's an orthogonal matrix. But here I'm not saying that the matrix is orthogonal. I'm saying it's an orthogonal projection matrix. And the difference between this and the general case is that it's not only that the range of P and the null space of B, their intersection is trivial. In fact, they are orthogonal. They are perpendicular to one another, which means that if you take any vector in the range of P and any other vector in the null space of B, their inner product is exactly equal to 0. Okay, so an orthogonal projection matrix, it has basically this additional feature that the range is perpendicular to the null space. In that case, you can show that you get another feature for the projection matrix. It also becomes Hermitian. So P is an orthogonal projector if and only if it is idempotent and it is Hermitian. Okay, and basically for orthogonal projectors, the spectral norm or the L2 norm is exactly equal to 1. Now, if you have a general matrix A and you want to project along the range of A, the column space of A, if you want to project onto the range of A along the orthogonal complement of the range of A. Okay, so suppose now that you have a matrix A which is not a projection matrix. So A may, again, to be projection matrix, it must satisfy that A squared is equal to A. Suppose that you have a general matrix A and you want basically to construct an orthogonal projection matrix that projects onto the range or column space of A along the orthogonal complement of the range of A. So last time I said that basically this projection matrix can be written in terms of the reduced SVD of A. So if A is equal to UA SVA Hermitian, then to orthogonally project onto the range of A, you need to use the matrix UA Hermitian. And the orthogonal projector onto the range of A, it has other forms. So I talked about them in the previous lecture, and one of them is this nice form, which is that the orthogonal, this nice form here with an inverse. Okay, so we are assuming that there is an inverse. It's valid for the special case in which the columns of A are linearly independent. In that case, you can show that basically UA Hermitian can be written as A. Then the inverse of A Hermitian A then multiplied by A Hermitian. And as I said, for you taking the wireless communications course, we will basically use this matrix, later in the course when we study MIMO channels. Okay, then if A happens to be just a single column, so if A is just m by 1, then A Hermitian A becomes a scalar, right? Because A Hermitian A is of size n by n, if A is m by n. And so if n is equal to 1, A Hermitian A becomes just the scalar, which is the L2 norm squared of vector A. And you will see that basically we can, now this thing is not really matrix inversion. It's just 1 over some vector, and of course, I'm assuming that this vector is anything but the zero vector. Okay, so this is a review of the previous lecture. Now, suppose that you are in the real space n by 1, and you want to orthogonally project onto a hyperplane. So for a hyperplane to be a subspace, it must pass through the origin, through the point, whose coordinates are all 0. So the equation of a hyperplane in the n-dimensional Euclidean space, such that this hyperplane goes through the origin, is this. So there is a vector eta. Eta transpose x is equal to 0. That's the equation of the hyperplane. Generally, the equation of a hyperplane will be eta transpose x plus p. Okay, but in that case, the hyperplane will not be a subspace because it does not include the all 0 vector. To be a subspace, you just need, basically this constant here to be equal to 0. Okay, so in the lecture here, I will basically talk about this case in which the hyperplane is indeed a subspace, and then in homework 3, I will give you, I will tell you, how to project onto this thing here, which is not a subspace, and it's a simple trick. Okay, so if you go, refresh your memory, what is actually the equation of the hyperplane? What is the meaning of this vector eta? Okay, so you have a hyperplane. Okay, so it's a plane in so basically in maybe this is a plane living in 3 dimensions. Vector eta or general, so this is general for a general n. This vector eta is a vector orthogonal to the plane. Okay, so eta, it has a sort of a physical meaning. It gives you a direction that is perpendicular to the plane, which means that if you take vector eta, and and it's clear from this equation, if you take vector eta and you basically do the dot product or the inner product with any vector in the plane, then you basically get A0. Okay, so how can we project onto the plane? So suppose that you have a general vector, and you want to project that vector onto the plane. So, if you want to project onto vector eta itself, this is the projector, right? So this is a special case from here. If you want to project onto a column vector, right? A matrix with just one column, the form of the projection matrix is, the orthogonal projection matrix is eta transpose over the L2 norm squared, which is eta transpose eta. So this guy alone will project onto eta, but you don't want to project onto eta, you want to project onto the plane. And so basically the projector to be used here is I minus eta transpose. Yeah, exactly. Yeah. So basically, this is what you do here. And again, like I will leave for you the case. What if the hyperplane is not passing through the origin? One thing also to mention is again a nice thing that we said that basically the least squares problem, its solution is that vector x. So you are given a and b. You basically want to obtain x such that this is minimized, and so the general solution is basically that x is equal to the pseudo inverse of a multiplied by b. Okay, and then if basically a has a non-trivial null space, then basically the optimal solution is not unique, and you can add here any vector from the null space of a. So what if you take ax, so a multiplied by the optimal solution? So ax together will be basically a multiplied by the pseudo inverse of a multiplied by b. And then what is, I said it in the previous lecture, what is a multiplied by the pseudo inverse of a? It is one form of an orthogonal projector onto the range of the matrix, right? So last time I said, it has several forms. One of them is UA Hermitian, and one of them is this one. You can show that this is also this. Okay, so it's like the optimal solution to the least square problem. Again, if you take a with the x, if you take ax, then it's like you are projecting vector b, the given vector b, along the column space or the range of matrix A, right? So this is what. So this again, these two matrices, A multiplied by the pseudo inverse of A, is a projector. It's specifically, it's an orthogonal projector onto the range of A along the orthogonal complement of the range of A. And what you are doing, you are applying it to vector B. So when you solve this least square problem, it is, you may think of it as if you are projecting B onto, basically orthogonally, onto the range of matrix A. Okay. So this is basically, the story of, projection matrices. Now, what if we start playing with a number of projection matrices? Okay, so my focus next will be just one example, and then in the homework you'll see others. What if I take two projection matrices and add them? So generally speaking, is this a projection matrix? So adding two projection matrices, will it give you a projection matrix, yes or no, and whether it's like a conditional yes, or every time it is a projection matrix? Okay, so now we will start dealing with these things. What will happen if you start mixing, projection matrices? Okay, any question? Okay. So suppose you have two projectors, and now those projectors may be orthogonal projectors, but not necessarily. Okay, so they may be just general projectors. Okay, so in other words, that it may be the case that the range and the null space of each of these two matrices, the range and null space, their intersection is just the O0 vector without necessarily being orthogonal to one another. Okay, so you start with two projection matrices. So you start with phi and you start with psi. And phi projects onto S1 along S2, and so S1 is basically the range of psi, and S2 is the null space of, is the range of phi, and S2 is the null space of phi, and psi is another projector that projects onto S3 along S4, which is another way of saying that the range of this matrix is S3, and the null space is S4. Okay, so just to make sure that we understand actually what is the meaning of being projector and so on. So those things mean the following. If you take a vector in S1, okay, if you apply matrix phi to the vector, you get the vector exactly. If you take a vector in S2, if you apply the matrix phi to X, then you get 0, right? Because S2 is the null space of phi, and S1 is the range of the projector. And by design, I mean, this is what we do when we design projectors, as I did in the previous lecture. You design them so that if you multiply the matrix by a vector living in the range, you get the vector exactly. And basically, the same for psi. Every vector in S3, psi x is equal to x for every x in S3, and for every x in S4, basically psi x is 0 because S4 is the null space of psi. Now, who is our friend here? Well, I mean, a matrix is a projector if and only if it is idempotent. Okay, and so if you sum the two matrices, phi and psi, one way to investigate whether this sum itself is a projector or not is simply to take this sum and square it and check whether the square is equal to the sum itself. Okay, so that's basically the plan. Take phi plus psi squared. Okay, so when you square it, you get 4 terms, and phi itself is a projector, so it is equal, so the square is equal to the matrix, the same for psi, but then you get cross terms. Okay, so this square here is phi plus psi, but then you have those additional terms, right? So if phi plus psi is a projector, so if basically this thing is a projector, it must be the case that it is idempotent, and so it must be the case that this square is equal to these two terms alone. And so this quantity here must be the O0 matrix. Okay, so if phi plus psi is a projector, so here the idea is that it must be idempotent. And in that case, the difference between the square and the sum of the square and the sum, is this matrix here. So it must be the all zero matrix. Okay. Phi ipsi plus ipsi, phi is equal to 0. Then multiply this matrix from the left by phi. So you get phi squared ipsi plus phi ipsi phi is equal to 0. Then phi itself is a projector, then its square is equal to itself. So we get that phi ipsi plus phi ipsi phi is equal to 0. Now go to this expression again, and now multiply it from the right by matrix phi. And so here you get ipsi phi squared, which is ipsi phi, and then you get basically this term here will be phi ipsi phi. Okay, so again, if our matrix is a projector, so this is equal to that. So the sum of these two matrices is the all zero matrix. Take this equation and then you basically do two, one time you multiply by 5 from the left, another from the right. And now look at these two equations here. Basically from the first equation, phi ipsi is the negative of this matrix, and ipsi phi is the negative of this matrix. And it's the same matrix here and there. So basically, combining these two equations, phi ipsi is equal to ipsi phi, they are both equal to this minus phi ipsi phi. But we have the sum of these two matrices, equal to the all zero matrix, and now we have shown that they are both equal to one another, and so basically 2 multiplied by matrix is the all zero matrix. 2 is just a scalar. It means that phi ipsi is equal to 0, and the other one is equal to it. So it means that this guy alone is 0, and this guy alone is 0. Okay. So what are we doing here? We are saying that if phi plus ipsi is a projector, again from examining the square of phi plus ipsi, we know that phi ipsi plus ipsi phi is equal to the all zero matrix. But then doing these steps, we actually showed something like something stronger. Which is, if this is true, and because phi and ipsi, each one of them is a projection matrix, and hence idempotent, it must be the case that this guy alone is equal to the all zero matrix, and this guy alone is equal to the all zero matrix. Okay? So now we have this theorem. Phi plus ipsi is a projector if and only if basically this is equal to 0 and that is equal to 0. Right, because look at from in the other direction, if this product is equal to 0 and n, and that product is equal to 0 and n, then the matrix is idempotent, then it is a projector. Okay, so this is the proof of one direction. The other direction is sort of trivial. I mean, if each one of those two guys is 0, then the matrix is idempotent, and hence a projector. Okay, so. So the answer to our question is a conditional yes. Okay, so if you take two projection matrices, two projectors, and then you add them, well, you get a projector, but you need a condition. Okay, so phi plus ipsi is a projector if and only if basically phi ipsi and ipsi phi both are equal to the all zero matrix. Okay, if this is true, then phi plus ipsi is a projector, and vice versa. So this is by examining, whether phi plus ipsi squared is equal to phi plus ipsi. But once you hear the word projector, I mean, a question comes to mind. Projector, so what is the range of this projector, and what is its null space? In other words, it's a projector onto what subspace, along what subspace? Okay, so this is the question. So projector, onto what and along what? Claim phi plus ipsi, if it is a projector and it needs this condition to be satisfied, it is a projector onto S1 plus S3 along S2 intersection S4, which is to say that the null space of phi plus ipsi is the intersection of S2 and S4. Remember, S2 is the null space of phi, and S4 is the null space of ipsi. And what is the range of phi plus ipsi? It's S1 plus S3. What do we mean by S1 plus S? What does it mean to add two subspaces? So S1 plus S3 is the subspace of vectors that can be written as the sum of two vectors, one living in S1 and the other in S3. Okay, so, to prove this claim, so again, the claim is that the range of phi plus ipsi is S1 plus S3, and the null space of phi plus ipsi is S2 intersection S2 intersection S4. And so we want to show that, we have this equality and they have that equality, and we know the trick. The trick is you want to show that two sets are the same, then you show that this is a subset of that and vice versa, and then you show that this is a subset of that and vice versa. Okay, so basically the coming steps are to show those inclusions and hence to establish that this statement here is true. Okay, so phi ipsi, again, now I am studying the case in which phi plus ipsi is indeed a projector. Okay, so it's indeed because if it's not a projector, then the question itself is meaningless. If it's not a projector, then I mean you cannot ask, it's projecting onto what. So it is a projector, and so phi ipsi is 0, the all zero matrix, and ipsi phi is the all zero matrix. Let's sort of try to think about these expressions. What do they really mean in terms of the relations between the subspaces S1, S2, S3, and S4? So if phi ipsi is equal to the all zero matrix, this means that the columns of ipsi are living in the null space of phi. And so this means that the range of ipsi is a subset of the null space of phi. So this means that S3 is a subset of S2. This means that S3 is a subset of S2, okay? So now we have, if ipsi plus phi is a projector, then phi multiplied by any vector in S3 will give you the all zero vector, right? So remember what was our starting point? Phi ipsi, so this is S1, S2, and so this is the range, this is the null space, this is the range, this is the null space. Now, initially, we say that, phi multiplied by any vector in S2 will give you basically 0, because S2 is just the null space of phi. And these two guys are related to ipsi. Now, if this expression is true, if phi ipsi is equal to the all zero matrix, now a relationship is established between S2 and S4, S2 and S3, sorry. S2 and S3, which is that S3 lives in S2, which means that if you choose now, so basically there is an inclusion here, if you choose a vector in S3, which is the range of ipsi, phi times that vector will give you the all zero vector. Similarly, ipsi phi is equal to the all zero matrix, so basically the range of ipsi is living in the null, the range of phi, the column space of phi is living in the null space of ipsi, which means that S1 is a subset of S4. So what will happen if you take a vector in S1 and multiply ipsi by it? Okay, then ipsi multiplied by any S4 is basically the null space of ipsi, and now we are saying that S1 is a subset of S4. So if you take a vector x in S1, ipsi x is the all zero vector. Okay. Now, of course, note that S1 intersection S2 is equal to 0. This is, from the very beginning, we said that phi is a projection matrix. So the range intersection the null space is just the all zero vector. Okay. So S1 intersection S2 is 0. So this is because phi is a projector. Phi is a projector, and S1 is the range of phi, and S2 is the null space of phi. So their intersection is just the all zero vector. And so S3 is living in S2, and the intersection between S1 and S2 is the all zero vector. So it means that the intersection between S1 and S3 is just the all zero vector. Okay, so let's now try to basically show those equalities here, and we will show those equalities by showing 4 inclusions. Okay, so let's do them one by one. Take a vector z in the range of phi plus epsilon. Being in the range means that there is a vector w such that phi plus epsilon multiplied by w is equal to this vector z. So z is equal to phi multiplied by w plus epsilon multiplied by w. What is phi w? Phi w is a vector living in the range of phi, which is S1. And what is epsilon w? Epsilon w is a vector living in the range of epsilon, which is S3. So if you start with a vector in the range of phi plus epsilon, this vector must be expressible as the sum of 2 vectors. One of them is in S1 and the other is in S3, and we have just said that S1 intersection S3 is just the all zero vector. So it means that Z belongs to this quantity here, S1 plus S3, which again is a notation to denote the subspace, the set of vectors that basically can be expressed as 2 components, one of them in S1 and the other in S3. So we have this inclusion. Now, take Z in basically S1 plus S3. So this means that Z can be written as the sum y plus y tilde. Y is in S1 and y tilde is in S3. Now apply phi plus epsilon to this Z. So you apply phi plus epsilon to Z, and Z can be written as y plus y tilde. So you get 4 terms. Okay, let's investigate the 4 terms. So phi y. Remember, vector y is in S1, which is the range of phi, and phi is a projector, so phi y is y itself. Okay, so this is this one. What about epsilon y? We showed that basically if the sum epsilon plus phi is a projector, then we get this nice relations, which tells you, for example, that epsilon multiplied by any vector in S1 will give you the all zero vector. So epsilon y is equal to 0. What about phi y tilde and epsilon y tilde? Y tilde is in S3, so epsilon y tilde is equal to, so S3 is the range. It's the range of epsilon. So epsilon y tilde is y tilde. And as we have shown above, phi multiplied by vector in S3 is equal to 0, because S3, if phi plus epsilon is a projector, it must be the case that the null space of basically it must be the case that that the range of epsilon is a subset of the null space of phi, and so this will be equal to 0. And so 2 terms are the all zero vector, the other 2 terms are y plus y tilde. So you take phi plus epsilon z, and what is z? Z is y plus y tilde. You get y plus y tilde. Okay, so so phi plus epsilon you apply to z, you get z. Which means that z can be expressed as phi plus epsilon times a vector. So z is living in the range of phi plus epsilon. So you start with the vector in S1 plus S3, you are guaranteed that this vector is in the column space of phi plus epsilon. And so we have this inclusion here, and those together establish the equality between the range of phi plus epsilon and S1 plus S3. Now, take a vector in the null space plus phi plus epsilon. So phi plus epsilon multiplied by the vector is equal to the all zero vector. Then phi z plus epsilon z is equal to the all zero vector. Now multiply both sides from the left by phi. So when you multiply both sides from the left by phi, and you have 2 things. So if you multiply by phi, you get phi z plus phi epsilon z is equal to the all zero vector, right? So what is phi? Well, phi is our starting point. Phi is a projector, so it's idempotent. So this is phi z. What about phi ipsi? If phi plus ipsi is a projector, it is a projector if and only if phi ipsi and ipsi phi are equal to the all zero matrix. So this will be the all zero matrix. So this is 0 again, and we are left with phi z equal to 0n by 1. 0n by 1. Okay, so if we multiply again, if we take this expression, multiply both sides from the left by phi, we end up with the all zero vector equal to phi z. So it must be the case that z lives in the null space of phi, which is S2. Now repeat, but now you multiply both sides of this equation from the left by ipsi, and you show that z is also in the null space of ipsi, which is S4. So if it lives in the null space of phi and also in the null space of ipsi, then it lives in their intersection, basically S2 intersection S4. So you start with a vector in the null space of phi plus ipsi, you end up with the vector in the intersection of S2 and S4. So we still have to do the other inclusion. Take a vector in the intersection. Okay, so it is the intersection. If it's in the intersection, then it is in S2 and it is in S4. If it is in S2, then phi z is equal to 0 because S2 is the null space of phi. And if it is in S4, then if psi z is equal to 0, then you sum these two equations and you get that phi plus psi multiplied by z is equal to the all zero vector. And so it means that z is in the null space of phi plus psi. So you start with the vector in S2 intersection S4, you end up with the vector living in the null space of phi plus psi. So we have the other inclusion. Okay, so basically, the conclusions from this slide is that phi plus psi is a projector if and only if phi psi is equal to phi is equal to the all zero matrix. If phi plus psi is a projector, then what is its range and what is its null space? The range is S1 plus S3, sorry, and the null space is the intersection of S2 and S4. Okay, and then again, like any problem, like this, will be solved like sort of in a similar way. You take the matrix, perhaps you you square it. So here in our case, we focused on psi plus phi, but you can do other things as you will see in the problem set. Okay, any question? Okay, so projectors we are not done with projectors, and actually projectors will play a role in in random matrix theory. Because in many cases we are interested in the distributions of quadratic forms whose matrix is an orthogonal projection matrix. Okay, so they will come again. But now we will turn our focus to the Perron Frobenius theorem. And the original theorem is by Perron, and it is basically a theorem in which you have a matrix that is a square matrix, real valued, and every element is strictly positive. Okay, so we are talking here about positive matrices. Positive, not positive definite or anything like this. Positive in the sense that each component, each element in the matrix is a strictly positive. Now, this matrix, it has a spectral radius, right? It's a square matrix. You can define for it a spectral radius. Simply, you go and compute the eigenvalues of the matrix. You compute the magnitudes of the eigenvalues, and the maximum magnitude is the spectral radius. Now, the spectral radius of a positive matrix is strictly positive. Okay, and one way of reasoning about this is that suppose that the spectral radius is equal to 0. So it means that the maximum magnitude for an eigenvalue is equal to 0. So this means that all eigenvalues are in fact equal to 0. So the sum of eigenvalues is equal to 0. So the trace of the matrix should be 0. But this contradicts the fact that the matrix has strictly positive elements. And so the elements on the main diagonal, their sum is strictly positive. Okay, so it cannot be the case that rho of A is equal to 0. Okay, so if the matrix has strictly positive elements, then its spectral radius is guaranteed to be strictly positive. Otherwise, you get a contradiction. Okay, so regarding those matrices, we want to make 4 claims. Okay, important, very important claims. And so one of them is that rho of A, the spectral radius, is an eigenvalue. It's not just the maximum magnitude for an eigenvalue. It is an eigenvalue. Okay, you know, just to remind you what is the spectral radius. Suppose that you have a matrix A with eigenvalues, let's say -1 and 1 and 1 plus I. Suppose that you have a matrix with those eigenvalues. What is the spectral radius, right? So the magnitude of -1 is 1, the magnitude of 1 is 1, the magnitude of 1 plus I is equal to square root 2. So what is the spectral radius? The spectral radius is square root 2. But there is no eigenvalue equal to square root 2, right? The eigenvalues are -1 and 1 and 1 plus I. So generally speaking, the spectral radius, it's the maximum magnitude, and you may not actually have any eigenvalue that is exactly equal to the spectral radius, like in this case. Square root 2 is the spectral radius, but it is not an eigenvalue. Okay, so for positive matrices, we will prove that for them, the spectral radius is an eigenvalue. Not only this, the spectral radius is an eigenvalue, and you can write down the associated eigenvector as a vector that is strictly positive, a vector whose components are strictly positive. Second claim is that there is no other eigenvalue for the matrix whose magnitude is equal to the spectral radius. So any other eigenvalue for the matrix will have a magnitude strictly less than rho of A. Number 3 and 4 basically tells us that rho of A, the spectral radius as an eigenvalue, is a symbol eigenvalue. So the geometric multiplicity is equal to 1, and the algebraic multiplicity is equal to 1. Okay, so those are conclusions that we can make regarding positive matrices. So where do we encounter matrices in which all the elements are strictly positive? So one domain of application, basically matrices in which the elements are probabilities. Suppose that all the probabilities in the matrix are strictly positive. So we will see this in Markov chains. So, Markov chains are characterized by something called the transition probability matrices. And, sometimes those matrices may have zeros, but, sometimes they have strictly positive elements. And so what we are saying here is relevant to something like, discrete time Markov chains. If you are doing wireless communications, what is an example of a matrix in which the guys inside the matrix are positive? Like if you have a matrix, let's say, of powers, right? So powers, perhaps transmission powers of users in the system or something like this. Then you will have to deal with a matrix that lives whose components are real valued, and all of them are strictly positive. So this theorem is very relevant to probability, to something like Markov chains. It's also useful in some of the power control problems in wireless communications. Okay, and of course, when we study those other things, these properties will be central, will be very important. Okay, but now let's go abstract, and how can we show this? So we start with basically showing that if A is strictly positive, this situation will not happen. If A is strictly positive, then rho of A is an eigenvalue. So here is basically how we will do it. Start with a specific eigenpair for matrix A. So there is one lambda for A whose magnitude is equal to the spectral radius of A. And there is an associated eigenvector, which is alpha. So basically write down this expression here, the Eigen Equation, A alpha is equal to lambda alpha. Again, here you write it for a specific lambda. The eigenvalue whose magnitude is equal to rho of A, is equal to the spectral radius. Now define another vector beta, and beta basically, it's basically the components. You take the components of alpha and you take their magnitudes. So beta here is the magnitude of alpha, and here what does it mean to have a magnitude of a vector? Here I mean to do it element-wise. So you visit vector alpha and you take the magnitude of each element in alpha. So beta is the magnitude of alpha element-wise. Now because beta is a vector of magnitudes, then we can say something about it. So we can say that beta as a vector element-wise, it's a non-negative vector. The components of beta are real valued and non-negative because it contains magnitudes. But we can also say something. Beta has at least one positive element. Okay, so beta, this is the meaning that beta is not equal to the all zero vector. Beta has at least one positive element. And why is this? Beta is the magnitude of alpha. Alpha element-wise, alpha is not an arbitrary vector, it's an eigenvector, and by definition, eigenvectors are not the all zero vector. The all zero vector is not a valid eigenvector, okay? And so it means that alpha, we are guaranteed to get some, components in beta that are strictly positive, okay? So because of how beta is defined, it is greater than or equal to 0 element-wise, and beta is not the all zero vector of the n-dimensional space. Now multiply A by beta. Okay, multiply A by beta and examine the ith component. Okay, so what is the ith component of A multiplied by beta? Well, what you do here is that you do a sum involving the elements on the ith row of matrix A. So basically, the ith component of A beta is summation j from 1 to n aij. So here we fix the row at I, and then we do the product. We multiply, the respective elements on that ith row with the components of vector beta. Okay. Now we can basically take aij and write something like this. Why? Because aij is real valued and strictly positive. So basically each aij is equal to its magnitude. And by definition, beta j is equal to what? Beta j is equal to the magnitude of alpha j. And so basically the summand here is the magnitude of aij alpha j. Now apply the triangle inequality. The sum of magnitudes is greater than or equal to the magnitude of the sum. Okay, so that's it, the triangle inequality. And so now we get this summation here, the summation j from 1 to n aij alpha j. So what is this quantity? It is the ith component in basically the vector A alpha. It's the ith component in the vector A alpha. And we know something about A alpha. A alpha is equal to lambda alpha. So the ith component in vector A alpha is basically equal to lambda alpha I, the ith component in vector alpha. And so this is the magnitude of lambda multiplied by the magnitude of alpha I. What is the magnitude of lambda? Again, we started with an Eigen equation, not with an arbitrary eigenvalue. We specifically focused on an eigenvalue whose magnitude is rho of A. So this is rho of A, and the magnitude of alpha I is beta I by how we defined vector beta. And so this is true for every I, for every component. So element-wise, we have this relationship. So if you multiply vector A, if you multiply matrix A by vector beta, okay, you get, and so on the one hand. On the other hand, you take vector beta and you multiply each component by the spectral radius of A. Then you get an element-wise inequality. each component in this vector is greater than or equal to each component in that vector. Okay, so to show that rho of A is an eigenvalue, we want to show that this inequality is satisfied with a strict equality. Okay, so desired, show that A beta is in fact rho A beta. Because if you write that, if you show this, then you are establishing an eigen equation with an eigenvalue rho of A. So you are basically showing that rho of A is indeed an eigenvalue for the matrix. And it's not like this situation here in which the spectral radius is something that is not an eigenvalue. Okay, so now we want to show that actually this inequality is satisfied with equality, and we will do the proof by contradiction. Okay, so here is the story. We will define y as the difference between these two sides. So y is A beta minus rho A multiplied by beta. Okay, now if y is the all zero, if y is the all zero vector, then actually we have A beta equal to rho A beta, and this is actually what is needed. But can y have a strictly positive component? Okay, so we want to show that this will lead to a contradiction, because if it leads to a contradiction, then it is nonsense, and the true thing is that y is the all zero vector, which means that A beta is equal to rho of A multiplied by beta. Okay, so basically the outline of the coming steps is like this. You take this quantity and you say, well, let's assume that vector y has at least one strictly positive component, which means that this inequality is not this. Show that there is something that does not make sense, and then it must be the case that y is the all zero vector, and we have our result here. We will use a simple idea. Suppose you take a positive matrix and you multiply it by a non-negative vector with at least one component that is positive. If you do this, you will get a strictly positive vector, right? So you have a matrix, right? So when you have a matrix that is strictly positive, so you have elements, okay? So you have elements, and those elements are strictly positive. Now you multiply by vector. This vector may have zeros, but suppose it has somewhere here, it has a positive element, okay, and then perhaps other zeros. So what will happen when you multiply each row in the matrix, and each row in the matrix again, each element is strictly positive by the vector. So some elements will be multiplied by zeros, but since the vector contains one at least a strictly positive element, it will be multiplied by strictly positive element in the matrix, and you get a strictly positive result. So a positive matrix multiplied by a non-zero non-negative vector. So it is a non-negative vector with at least one positive component. This is guaranteed to give you a positive vector, a vector whose components are strictly positive. Define Z to be equal to A beta. Define Z to be equal to A beta. Okay, so again, just to recap here, that we started with A alpha is equal to lambda alpha, and lambda is an eigenvalue such that the magnitude of lambda is equal to the spectral radius of A. Then we defined vector beta to be the magnitude of alpha elementwise. So define Z to be A beta. It means that Z is the product of a strictly positive matrix by a vector, and we said that vector beta is non-negative because it contains magnitudes, and because those are the magnitudes of the components of an eigenvector, the eigenvector cannot be the all zero vector, so beta must have at least one element that is strictly positive, and so Z is a strictly positive vector. Under our assumption, AY is also equal to 0, so this is under our assumption that Y has at least one strictly positive component. Okay, so y, which is a beta, remember that y is a beta minus rho of a beta. So ay is greater than 0 element wise, and z, which is a beta, is greater than 0 element wise. So we will do here a, one of those steps that, that looks like very weird, but these are the things that move the, that smart people do to like move the proof forward. So claim if you have two strictly positive vectors. Okay, so the vectors I'm talking about here are basically vector z and vector ay. Okay, so a beta and ay. You always find a strictly positive epsilon such that one of those positive vectors, and here I will take it to be ay, is strictly greater than, and this is again of course to be interpreted as element-wise, epsilon, which is this positive constant multiplied by z. You can always do this. Okay, so here is the idea. What is the epsilon? So basically vector ay is strictly positive. Vector z is strictly positive. And so what you can do is the following. You take each component here divided by the respective component there. So you take the ith element in ay and the ith element in z, and you take the ratio, and then you choose epsilon to be the less than the minimum. Okay, so you choose epsilon to be less than the minimum. So what is this thing? So epsilon is less than the minimum over I of AYI over ZI. And the minimum is less than or equal to what? AYJ for every J divided by ZJ, because this is the minimum. And so what do we have here? This is a strict inequality. So we have that AYJ for every J is strictly greater than epsilon ZJ, which means that AY is greater than epsilon Z component-wise. So if you choose an epsilon satisfying this, any epsilon from 0, so it's greater than 0 and less than this minimum, this epsilon actually will tell you that vector ay is greater than vector epsilon z. Okay, so now we know, so basically z is a beta, so don't forget that z is a beta, and y is a beta minus rho of a beta. And so what you do basically here is that you rewrite ay greater than epsilon z, you rewrite it using these two expressions here. Okay, and so you get that az minus rho az is greater than epsilon z. You can move this term to the other side. You get az greater than basically the spectral radius plus epsilon multiplied by z. Okay, and then this is a strictly positive quantity. You can divide both sides by it, and then you have this inequality. Okay, so now we have the inequality in terms of this strictly positive vector z. It tells you that we have a matrix. So what is our matrix here? It's matrix A. It's matrix A scaled by 1 over rho of A plus epsilon. We have seen this before. Remember in the proof of Gelfand's formula, which relates the spectral radius to basically matrix norms. So we encountered the exact same matrix in which you take a matrix A, it has a certain spectral radius, rho of A. So if you divide matrix A by rho of A plus epsilon, then you get a matrix whose spectral radius is strictly less than 1. Okay, so remember this story that rho of 1 over rho of A plus epsilon A, the spectral radius of this matrix, is strictly less than 1. Okay, and remember the story about matrices whose spectral radius is strictly less than 1? If you raise those matrices to higher and higher powers, they diminish, their components diminish. In fact, they go in the limit to the all zero matrix. Okay, so here we constructed this, basically this inequality with matrix A multiplied by 1 over rho of A plus epsilon. So this, if you take this scalar with the matrix, now we have at our disposal a matrix whose spectral radius is strictly less than 1. Okay? And so multiply this this expression here, multiply from the left by this matrix. Okay, so we have this, multiply by this matrix. Okay, so you multiply 1 over rho A plus epsilon A Z. Okay, and the other side will be 1 over rho A plus epsilon A. So that's the matrix multiplied by the vector. You can easily convince yourself that basically when we multiply both sides of this inequality by this matrix here, the inequality is preserved. The inequality is exactly preserved as a strict inequality. But this guy itself is greater than Z. So basically, the square of the matrix multiplied by Z is strictly than Z. Do this repeatedly. And if you do this repeatedly, then basically what you are showing is that this matrix to the power n, multiplied by Z is strictly greater than Z for every natural number n. Now take the limit of both sides as n goes to infinity. You can do this. You know, you can, if you have an inequality, you know, that is valid for every natural number, then the inequality is valid if you take the limit as n goes to infinity. You just need to basically change one thing, that if your starting inequality is strict, you need to include the possibility here that it is greater than or equal to. Okay, so this is exactly what we will do here. But what is this limit? You know, so this limit, there was this theorem that if a matrix has a spectral radius strictly less than 1, then the matrix raised to the power, I think this is like, n is the dimension. Okay, so the matrix is n by n. So again, this is like sort of, it's a bad choice. So let's call this v, okay, for every v. And so you take the limit v goes to infinity to the v, and this is v. Okay, so this will go to the all zero matrix. The other side does not depend on v. Okay, and so you get z. And so in the limit, you get this thing here, that z is less than or equal to 0. But what is vector z? Vector z is A beta. A is a matrix with strictly positive elements. What is beta? Beta is a non-negative vector. It may have zeros, but it must have at least one positive element because it's derived from an eigenvector. And so this product is strictly positive. But now we are shown under the assumption that y, remember y which is equal to A beta minus rho of A beta, under the assumption that y has at least one positive element, we get that z is less than or equal to 0. That's a contradiction. So our assumption is wrong. And so y cannot have any component that is strictly positive. Y is the all zero vector. So A beta is equal to rho A beta. So indeed, rho of A, the spectral radius of a matrix that is real valued and whose elements are strictly positive, rho of A is an eigenvalue. It is guaranteed to be an eigenvalue. And moreover, basically, the associated eigenvector is beta, and our starting point was that beta is non-negative. No, beta is actually positive. Beta is actually, we can say now that beta is strictly positive. No zero elements. How can we see this? Just to divide both sides by rho of A. Remember that, you know, the matrix with strictly positive elements, its spectral radius is strictly positive. The spectral radius cannot be 0, so you can divide both sides by rho of A. So you have beta equal to the 1 over rho of A beta. Now A beta is strictly positive because beta is non-negative and it has at least one positive component. So A beta is strictly positive, and we are dividing by a positive number. And A beta over rho of A is beta itself because we established this equation. So beta is strictly positive. So not only row of A is an eigenvalue, the associated eigenvector is an eigenvector with a strictly positive components. Again, a result, it's not just a theoretical result. Again, you can like be in a wireless communication system and you are solving, and matrix A has powers and you are solving a system of equations, and you want a guarantee that your solution makes sense in terms of being physical powers. So those should be positive. And so you will find Perron Frobenius Theorem helpful. So it tells you that, matrix A with a strictly positive elements, it has the spectral radius as an eigenvalue and the associated eigenvector is positive. Okay. Now, is there another eigenvalue? Okay, so is there lambda such that magnitude lambda is row of A and lambda is not row of A? Okay, so is there an eigenvalue for this? Because it may be, till now we haven't answered this question. We started with a lambda. Our first step in the proof is basically A alpha is equal to lambda alpha, right? So we took basically a vector. We took a vector. Alpha is an eigenvector associated with lambda, and lambda was an eigenvalue such that magnitude of lambda is equal to row of A. And then we use that, we use basically this vector beta, which is the magnitudes of alpha, to show that actually we have another Eigen equation, which is A beta equal to row of A beta. But can we actually have this one with a lambda that has a magnitude equal to the spectral radius, but lambda itself is not equal to the spectral radius? So suppose that you have in the complex plane, this is row of A, and suppose that there is a lambda that, let's say, is here. So this lambda, it has a magnitude that is equal to row of A, but it is not equal to row of A. So here is the good news, no. Okay, so let's see. So let's see why is this the case. One step above we did was basically to establish A beta greater than or equal to row A beta. Remember this thing? Actually, we got the inequality by one application of the triangle inequality, right? So we say, okay, we constructed vector beta. We investigated the ith element in A beta. Okay, and then we applied once the triangle inequality, and then this is what led to A beta greater than or equal to row A beta. But then we did a proof by contradiction to show that actually this inequality is strictly satisfied with equality. Okay, so it means that this triangle inequality is satisfied with a strict equality. And so what is the condition? If you have a bunch of complex numbers, when is this thing equal to basically this thing? The magnitude of a sum is equal to sum of magnitudes. So we have equality if and only if all zi's have the same angle. Okay? So for example, if all the numbers are positive, you get equality in the triangle inequality. If all the numbers are negative, you get the triangle inequality satisfied with equality. If all the complex numbers, they have e to the I pi over 3, if all of them have e to the I pi over 3, then the triangle inequality will be satisfied with a strict equality. Okay, so by contradiction, we prove that actually this is satisfied with equality, which means that actually we have a triangle inequality that is satisfied with strict equality. Okay, and so this means that, so this is the triangle inequality, and now it is equality. And so it means that those alphas, they have the same angle. So each one of them may have a different magnitude, and the magnitudes are betas, but they should have the same angle. Otherwise, the triangle inequality is not satisfied with equality. Okay, so this is very nice because it tells you that if you write alpha, so alpha is alpha 1, alpha 2 to alpha n, and each of these complex numbers is a magnitude and phase. So this is magnitude alpha 1 e to the I phi, magnitude alpha 2 e to the I phi also, not phi 1 and phi 2 and so on, because we have the triangle inequality involving the alphas is satisfied with a strict equality. And so basically this e to the I alpha can be, it's a scalar. You can put it outside. And what is remaining are the magnitudes. And so those are beta, vector beta. So alpha, so in fact in our proof, we started with A alpha equals to lambda alpha. Now we took the magnitudes of the alphas to get the betas. Now we can say something more about the relationship between alpha and beta. Alpha is beta multiplied by e to the I phi, which is a constant, some real valued phi. If phi is 0, then alpha is beta. If phi is pi, then this is alpha is minus beta, and so on and so forth. So alpha is a complex scalar, generally multiplied by beta. Okay, so we started with this. Eigen equation. Now I can write alpha is equal to e to the phi beta. Okay, I don't know why I added the minus sign. So basically a alpha lambda alpha, so this is plus, so replace this alpha by e to the I phi beta, and this alpha e to the I phi beta, and then e to the I phi is a non-zero number, right? It's a number living on the unit circle. Divide both sides by this number, and you get a beta equal to lambda beta. A beta is equal to lambda beta. Okay, so we started with a alpha equals lambda alpha with magnitude alpha equals rho a. Then we derived that a beta is equal to rho a beta. And now we are saying something more. We are saying that a beta is equal to lambda beta. Okay, so beta is an eigenvector associated with lambda. It's a scalar multiple of alpha. So beta itself again is an eigenvector associated with lambda. So it must be the case that lambda is equal to rho of A. It's not just that the magnitude of lambda is rho of A. Lambda must be rho of A. Because something, I am sure that like you took in a first course on linear algebra, that if lambda is different from A, okay, it must have an eigenvector linearly independent of beta. Okay, so we have a theorem that eigenvectors associated with distinct eigenvalues are linearly independent. So if lambda is different from rho of A, so it's equal to rho of A just in magnitude, but they are different as complex numbers, then it must be the case that alpha and beta are linearly independent, but they are not. Alpha is just e to the I phi multiplied by beta. It's just a constant multiplied by beta. So lambda is equal to rho of A. So any eigenvalue you start with a magnitude equal to rho of A is in fact equal to rho of A. So we establish our first result. Okay, very interesting that a strictly positive matrix, it has its spectral radius as an eigenvalue, and the associated eigenvector is strictly positive. And then we should claim too, no other eigenvalue of A satisfies this. Okay, the other eigenvalues of A will have a spectral radius, will have a magnitude strictly smaller than the spectral radius. Okay, so now it remains to show that basically the spectral radius as an eigenvalue is a simple eigenvalue. Before moving, basically you may hear, some people, rho of A in our context here, sometimes it's called the Perron root. Okay, Perron Frobenius eigenvalue, leading eigenvalue, dominant eigenvalue. Okay, so in the papers and in books, basically different names given to basically this row of a matrix that is strictly positive. Okay, any question? Lambda over row of A must be real? I don't understand. What lambda? Row of A radius. So it's the for a general square matrix A, you do eigen decomposition, you obtain the eigenvalues. In our case here, yes. Okay, so that's the conclusion. Yes. In this case, in which matrix A, so remember, A is a matrix with strictly positive elements. Yes, that will be true. Basically, the maximum eigenvalue will be a real valued positive quantity. Yes. In this case, okay, in this case, and that is Perron's basically theorem. Okay, so we are left with basically showing that that row of A is a simple eigenvalue, and here I will sort of be quick. So I will give like sort of the outline of how to show it, and the details are in the notes. So you do this in two steps. The reason you do, to show that an eigenvalue is simple, one way of proving it is just to prove that the algebraic multiplicity is 1, because we know that for any eigenvalue, the geometric multiplicity is less than or equal to the algebraic multiplicity. So if the algebraic multiplicity is 1, it must be the case that geometric multiplicity is 1. Okay, so you may wonder, why is this guy basically showing first that the geometric multiplicity is 1 and then showing that the algebraic multiplicity is 1? Well, because the proof that the algebraic multiplicity is 1 is a proof by contradiction, and it involves contradicting the fact that the geometric multiplicity is 1. Okay, so basically the outline here is show that the geometric multiplicity of row of A is equal to 1, then show that the algebraic multiplicity of row of A is 1 via contradiction. And what we will contradict is this fact here, via contradiction. Okay, so because like you may have done some exercise in the past in which like you were required to show that some eigenvalue is simple, and you said, well, I just proved that the algebraic multiplicity is 1. Okay, so that's the reason here. Okay, and of course, I don't know, perhaps there is a proof, a direct proof that that the algebraic multiplicity is 1, but this is what I know. Okay, so you start with proving that the geometric multiplicity is greater than 1. So showing that the geometric multiplicity is 1, you also do it by contradiction. You say, okay, let's suppose that the geometric multiplicity is greater than 1. So what does it mean that the geometric multiplicity is greater than 1? It means that there is another eigenvector, that is associated with row of A, and that is linearly independent of row of A. So if the geometric multiplicity is equal to 1, then there is something A eta is equal to row of A eta. And eta, so basically eta and beta are linearly independent. Okay, so this is true if the geometric multiplicity is indeed greater than 1. we will assume here that eta, this other vector, is real with at least one strictly positive component, and the argument is in the notes. Okay. Then we will basically play with beta and eta. Okay, so you are saying that there is another eigenvector that is associated with rho of A. Okay, so let's basically construct this vector. Beta minus C eta. And C is a positive constant that is chosen such that beta minus C eta is non-negative, and it has at least one entry, one element that is equal to 0. Again, you can make a simple argument that I will leave for you, that you have a vector beta, and then which is strictly positive. Vector eta, it's real and has at least one strictly positive element. You can choose a positive C such that beta minus C eta is non-negative, and it has at least one element that is equal to 0. And it cannot be the case that beta minus C eta is equal to the all 0 vector. Can this be true? Can this be true? So can it happen that you are basically adjusting the value of C so that you get a 0 in the vector beta minus C eta? Can you accidentally make no? Why no? Because remember, under our assumption, yes, under our assumption, beta and eta, exactly, that's the word, linearly, by our assumption, we are assuming that the geometric multiplicity is greater than 1, which means that there is another eigenvector that is linearly independent of beta. Okay, so by this assumption, it's guaranteed that beta minus C eta will contain a 0 by design, but it cannot be the all 0 vector. Otherwise, we will contradict the linear independence assumption. Okay, so here is basically the stool. Take beta minus C eta. So this is equal to A beta minus C A eta. Now beta is an eigenvector associated with rho of A, so A beta is equal to rho of A beta. A eta is the same. Okay, so A eta is also equal to rho of A eta. Take rho of A as a common factor, so A multiplied by beta minus C eta is equal to rho of A multiplied by beta minus C eta. Rho of A is strictly positive. Divide both sides by rho of A. So beta minus C eta is equal to this. So remember the story. Beta minus C eta is a non-negative vector. By design, it has at least one 0 component. It cannot have all the components equal to 0. A is a strictly positive matrix. A strictly positive matrix multiplied by a non-negative vector with at least one positive component gives you a vector that is strictly positive. You divide by rho of A, you get something that is strictly positive. So beta minus C eta is strictly positive. But by design, we choose a C to have a 0 in that vector. So that's a contradiction. So there does not exist an eigenvector linearly independent of beta. So the geometric multiplicity of rho of A is 1. It is exactly equal to 1. Okay. Now, what about showing the algebraic multiplicity is 1? Now, a comment. Okay. Now, suppose that you talk about matrix A transpose. So if you have a matrix with strictly positive elements, then it's a transpose has strictly positive elements, right? So everything that I said about A is applicable to A transpose, right? And what is the relationship between the eigenvalues of a matrix and its transpose? they are exactly the same, right? Because we don't do this numerically, but conceptually we obtain the eigenvalues via solving the characteristic equation, right? So you do this thing, right? Determinant lambda INN minus the matrix, right? You equate this thing to 0, you get the roots, okay, conceptually, and this will be the so-called eigenvalues of the matrix. Now, what about the characteristic function of the transpose? Okay, well, you take the transpose of this quantity, the transpose of I is I, and the determinant of the transpose is equal to the determinant of the matrix itself. So the characteristic function of the transpose is the same as the characteristic function of the matrix itself. So a matrix and its transpose, they share the same eigenvalues. So matrix A transpose, it's strictly positive. Transposition will not change this fact, and rho of A is an eigenvalue, and it is associated with an eigenvector that is strictly positive. So all our previous conclusions are applicable to A transpose. Moreover, because A and A transpose share the same eigenvalues, in fact, rho of A is also, it's basically the spectral radius of A transpose, and it is an eigenvalue of A transpose. Okay. So what is the associated eigenvector? There is a positive eigenvector associated. So I will call this eigenvector pi transpose. Okay, so I will define pi to be a row vector, and again, A transpose is a strictly positive matrix, so A transpose multiplied by some strictly positive vector will also give you rho of A multiplied by that vector. Okay, so rather than like doing things with A transpose, just transpose both sides and you get this. Okay, so it's like, sometimes, so rather than working with the transpose, sometimes we work with the so-called left eigenvectors. Okay, so it's a matter of taste. Okay, and left eigenvectors are important because, like, by the notation used in some fields, you have a row vector multiplied by the matrix. So we will see this in Markov chains. The convention is just to do something like this. Okay, so it's not a problem. Okay, if you just like the matrix multiplied by a column vector, then just take the transpose. Okay, but it's not bad also to get used to this Eigen equation with a left eigenvector. So right, pi is called a left eigenvector. Left eigenvector. Okay, so basically, okay, I don't think I have like time. I will not continue actually this proof. So it's, this is not even like a complete proof. So my conclusion is just keep this in mind. There is a left eigenvector associated with rho of A. Okay, the rest of the proof is like, you always learn by reading proofs. You learn something. Okay, so the proof is detailed in the notes. Here it's also partial, but in the notes it is like a full proof. And so you can basically continue doing it, but again, keep in mind this idea about that A transpose, you can play the same game with A transpose, and there will be a left eigenvector associated with rho of A. So what I will do at the beginning of the coming lecture is, what if zeros start creeping into our matrix? What will happen? Will we have like sort of a total collapse of the Perron theorem? Okay, so it was Frobenius, mathematician Frobenius, who started basically thinking about what if there are some zeros. Okay, I will not again go into details. I will just tell you some of the results. I think the main proof in this lecture is enough for this part of the course. So we will I will give you like sort of the results regarding non-negative matrices in which you allow the presence of zeros.